In this video, I'm going to talk about the gravitational energy associated with an object in a stable orbit. And I'm going to talk about actually three different energies here, and I'm going to see how they're all related to each other. And there's some nice relationships that work out with these energies. So first of all, binding energy we're going to consider to be the total energy of an object in a stable orbit. The binding energy will be negative because it's still bound to whatever it's orbiting, the planet or whatever it is. And so we can also view the binding energy as the amount of energy that we would have to pay into this object to get it completely out of the orbit and come away from the planet or whatever it's attracted to. We're going to have some kinetic energy. Remember that to have a stable orbit, this satellite, whatever kind of satellite it is going to be moving very quickly. So we're going to have to have a lot of kinetic energy associated with that fast motion so that it can stay falling away from the Earth at the right rate, or falling toward the Earth at the right rate, sorry. And then finally, it's still trapped by some large object like a planet or whatever it's orbiting, and so it's still going to have gravitational energy associated with being trapped in that object's gravitational potential well. So let's look at how these things are going to be related to each other. First of all, the binding energy, or the total energy, is going to be equal to the kinetic energy plus the gravitational energy. What I'm going to show is that the kinetic energy is actually going to be equal to negative 1/2 of the gravitational potential energy, and we'll still be using our formula for our gravitational potential energy. But because we have this relationship, I'm also going to show that the binding energy is going to be equal to, if I substitute this expression, which I haven't proven yet, but I will, negative 1/2 plus a whole is positive 1/2. So the binding energy is going to turn out to be equal to 1/2 the actual gravitational energy associated. To be careful with this, we need to make sure that we remember that this is for an object in a stable orbit. None of this would be true for an object that's resting on the ground. This is only for things that are moving really, really fast, orbiting the Earth so that they're moving so fast that they stay, they fall towards the planet at the same rate that the horizon falls away, and so the object stays in a perfectly circular orbit. So let's start by proving this. To get a stable orbit, we're going to assume that our object is moving in a perfect circular motion, and that perfect circular motion is being generated by the force of gravity. We're going to use the big formula for the force of gravity, and we're going to use me to represent the mass of the Earth, ms to represent the mass of the satellite, whatever it is that's orbiting. And we're going to use the big formula because this object is orbiting, so we're going to assume it's a substantial different distance away from the Earth. For this particular example, I'm going to use this formula for centripetal motion just because it works out nicely for what I'm trying to show. Now I have the mass of the satellite on either side, and the mass of the satellite can't be 0, or this isn't interesting, so I can divide both sides knowing that it's not a 0. And similar, the radius can't be 0, or else it wouldn't be an interesting problem. So I can divide out these radiuses as well, and I get a simpler expression for v squared. Now, since v squared is in my kinetic energy formula, this is a useful spot to stop when considering the forces acting on my stable orbit object. So I get 1/2 ms v squared, since it's the satellite's kinetic energy that we're interested in. So 1/2 mass of the satellite, but I can substitute my expression for v squared here, g me over r. So I get 1/2 times g ms me over r. And if you compare these two, what's interesting is that this is very similar to the gravitational energy formula. It's just the wrong sign. So if I take this and I multiply everybody by -1, I can get a good agreement between my two equations. So now I can substitute here. And then just bringing the negative out front, I can see that my kinetic energy is -1/2 of my gravitational potential energy. So that sort of, if I have that, then I can go ahead and do this, and I get three nice expressions associated with all of the energies of an object in stable orbit. I have the binding energy, which is the total energy, which works out to be just half of the gravitational potential energy. I have the gravitational potential energy. And then I have my relationship. If I'd like to know what my kinetic energy is, it's going to be -1/2 my gravitational potential energy. So those are just some general expressions of energy of stable orbits. Now I'm going to do some problems where I put some specific numbers to this, and we can look at what these energies look like and how they're all related to each other. There's going to be some trickiness with interpreting signs here, but as long as we're careful with our negatives, everything will work out. So that is gravitation. That is energy in a stable orbit.